So, dear participants, can you hear me now?
Yes, sir.
Yes, sir.
Yes.
So now I'm going to invite Dr. Amod Omarikar. He is associate professor at IIT Indore. So very soon he is going to join. So I request you please remain connected. I'm inviting him. Okay. Sir, can you hear me?
Yes, yes.
Okay. So shall I start?
Yeah, yeah. You can start.
Okay. So, dear participants, now we have the second speaker of the today.
some network problem? I'm not able to hear. हेलो सर, आप म्यूट है.
Okay. So there was some internet issue. So in the IIT Indore as the assistant professor in 2009 and presently working as the associate professor in the Department of Electrical Engineering. He is one of the founder members of the IIT Indore, and he's, other than the teaching and research, he has contributed lots in the education administration also. He served as a head school of engineering at IIT Indore, associate dean of the academic affairs, and presently he is working as a dean of faculty affairs. His main research interest includes application of power electronics, renewable energy system, power quality, and smart grid. So this is brief related to Dr. Amod. Now I will request to Dr. Amod, please hold the fort and start the session.
Yeah.
Thank you.
Thank you, Dr. Arvind, for inviting me for this session. Okay. I'll be surely happy to share some of the thought on how to design a standalone photovoltaic system, which is also one of my research area. So we are working on converter design and of standalone photovoltaic system. So I'll have a brief session here about the standalone photovoltaic system, how to design what are the design considerations of standalone photovoltaic system. And then I'll look into some simulations of some solar photovoltaic system, where we'll understand the concepts of MPPT and how to simulate that. And we'll have a brief look into it. Okay, and what is the concept of MPPT, and which is related to standalone photovoltaic system. So I'll just first I'll share the screen with you. So are you able to see the screen?
No, it's not coming now.
Now?
Now it's coming. No issue.
Okay. So these slides are kind of a guidelines. I'll switch off my video, sir, because some bandwidth issue comes, then it will not be.
Yeah. You can. No issue.
Okay. So let us see what is the design and simulation of standalone PV system. Before that, we'll have a parallel, means kind of some problems also we'll solve. Okay, in parallel, means how to design. So some design problem we'll take, and we'll also try to parallelly solve the problem so that it will be more clear to you, rather than just a presentation. I would like to present some example also, while numerical example, so that we'll have some idea about how to design a standalone photovoltaic. Okay, so what do you mean by standalone photovoltaic? So standalone definition, generally, a standalone PV system is a power source dedicated to some load, such as water pump, refrigerator, or radio transmitter. This is very vague definition. Okay, but mainly we understand from the term standalone is the PV or storage system, photovoltaic plus storage system. That is the only source from which the load may draw power. So standalone itself says that there is any other supply. Okay, so standalone can be also wind. Wind also can be a standalone. Okay, but there of course need to have storage, because all renewable energy sources, most of them are intermittent sources. Okay, so they are available sometimes, they are not available sometimes. Hence, we have to take that some storage elements, okay, to support the load whenever the source is not there. Okay, so we have to have a lot of design issues in this. We have to study when we combine photovoltaic and storage, and that is called as standalone. And other term is called as grid connected. So wherever grid is available, so we connect grid, but it's a combination. So whenever PV power is more, the load will be supplied by PV power. And when there is a deficit of power supplied to the load from PV, then rest of the power will be fulfilled by grid. Okay, so that's also one of the combinations generally. So we'll mainly focus on the standalone. So the typical standalone PV system is generally we have solar PV panels or array. Okay, then we'll have kind of a charge controller. Okay, then there is a DC load. Okay, then this charge controller. Why the name charge controller? It will control the charge to the battery. Okay, and also it will regulate the DC voltage. Okay, it does two things. It can regulate DC voltage. It can regulate the charge. Okay. Then this DC voltage will be given to inverter, which will supply the AC loads. Then there will be DC loads, okay, which will be supplied by the directly by battery. Okay. The battery can be of any rating, in the sense depends on the load and requirement. Okay. So solar PV, so we have to study multiple aspects like solar PV, then battery. Mainly we will focus on these two aspects, solar PV and battery. And some of the things we'll discuss about charge controller or the intermediate DC to DC converters. Okay. So this is a typical standalone photovoltaic system. So how is the power flow? Power flow will be generally from, let's say this is the main source of power. Okay. If this is the main source of power, this is PPV.
Excuse me, sir. Excuse
Yes.
me, sir. PT is not moving, sir. You're in the second slide itself.
Oh, okay, okay. Just a minute.
Sir, please make it full screen also, sir.
Yeah, I made it full screen. I don't know why it is not coming. Now you can see.
Yes, sir,
This
we
slide?
can see it.
Okay, now you can see full screen.
Yeah, but
No, sir,
okay,
no,
sir.
it is not full
No,
screen.
sir. Actually, you're sharing the screen instead of PPT. Okay, it's okay, sir. You can see it.
No, I had
No
to share
problem.
the screen because I have to show the simulations also. Okay,
Okay,
that's why I'm
okay,
sharing.
sir. No
Yeah.
issue, sir. No issues.
Okay, what I will do right now, I will do whenever simulation comes, I will share the screen. Okay, what I will do is right now I will share PPT only, but I have to share two PPTs, so that's why I am sharing this.
Okay, sir.
In
No
parallel-
issue, sir.
Okay, so now you can see this
Yes, sir. We can see.
full screen. You cannot see.
Yeah, it is full screen only, but yeah,
Okay.
your screen we can see as full screen.
Okay. Okay.
Okay, sir.
Fine.
Thank you, sir.
So there is a PPV from where the PV power will come. Okay. Then charge controller will process this power mainly to control this power. It will decide whether it will run in maximum power or some other operating point. So it will decide whether which operating point is solar PV panel will operate. Okay. Then this also will control the output DC voltage here, which will be also connected to a DC load is connected to that this output voltage. So the job is also to regulate this VDC. So this PPV will come, then some of the power will go here, okay, and rest of this will be charging here. So charging energy will go, and rest of the power will go here. Okay, so when PPV is 0, all the power will be supplied by the battery. So this you must be knowing all. Okay, so all this power as well as the DC power will be supplied by the battery. Now, next part. So what are the design steps in a standalone typical photovoltaic system? Okay, so first we have to identify what is whether there is a solar PV power available at the particular place. It is very obvious. Okay, then what is the consumption we are designing? Means what is the consumption for which we have to design the system, and what are the essential electrical loads? Okay, so this first we have to do the study whether the solar PV power is available, whether the electrical consumption is there properly, what are the type of electrical consumption, and then what are the essential electrical load. Okay, then next part comes as battery selection. So we have to select the proper battery based on the first step. So first step only will decide how to select the battery based on first and second step. So this is first step. This is second step. And based on first and second, third step will come, which is PV array sizing. Okay. So PV array sizing is main thing where we can, where most of our job is done. Okay, then module and charge controller will are obvious step. So we'll mainly focus on this first three steps. Okay, and then we'll see something about charge controller. Okay, module is depends on what is the PV array sizing. So if module also will decide the area of overlap. So mainly PV array sizing will decide the area, and based on that, then we can decide the modules. Okay, now what is solar availability? The first step. Okay, so insolation. So with the one term we always use in the solar PV systems, that is insolation means incident solar radiation. So we can see that this short form of incident solar radiation. Okay, so typical value for this over Earth is 1 kilowatt per meter square. Obviously, somewhere it is the average value. At some places it is lesser, some places it is higher. There is another term called irradiance. So it is an amount of solar energy received on a unit surface expressed in unit of kilowatt hour per meter square. Okay. Note the difference. Insolation is power. Okay, and this is an energy. Okay. So this is energy, amount of solar energy received per meter square. Okay. That is irradiance. So actually, this is a solar insolation. Okay, integrated with respect to time. So we can see that this is 1 kilometer per meter square, and this is 1 kilowatt hour per meter square. Okay, so based on that. Okay. So that is irradiance. Are you seeing the moving up slides? This slide you are seeing or not? Solar availability.
No, sir. We are still in the third slide.
Okay. Why I don't know why it is problems coming. Now you can see.
Yes, sir. It's
Okay,
moving.
this slide you have seen earlier. Standalone PV
No.
storage. Oh, okay. I'll again
Now
tell
only
you.
we are seeing.
Oh,
Okay,
okay. I'll keep this only because. Okay, now you can see slide zoom.
Slide 4. Yeah, zoomed.
Okay. Then at least instead of full screen, I will do it zoom only. Okay. So typical standalone PV system, we can see that evaluation of solar availability, electrical consumption, essential electrical loads. Okay. And then second step is battery selection, and third step is PV array sizing. So these first three steps are main steps in design of standalone PV system. Then rest of the steps will fall in place automatically. But first three steps should be accurate. Okay. So we'll mainly focus on these first three steps. With some examples we'll take along with it so that it will be clear to you how to choose. Okay. So we'll take very simple examples. So now what is insolation? So insolation, the first step, solar availability, whether we have the solar power is available at that place or not. Okay. So first step is insolation. So what is insolation? So insolation is incident solar radiation. You can check this incident solar radiation. Okay. So it is called as insolation. So typical value is 1 kilowatt per meter square. Okay. And irradiance, it is an amount of solar energy received on a unit surface expressed in unit of kilowatt hour per meter square. Okay. So solar irradiance is essentially the solar insolation integrated with respect to time. So these are the two definitions which we use frequently in the solar PV design systems. Okay. So we'll briefly see what is insolation at and how to find out insolation at any location. So for finding out insolation at any location, we should know what is the day of the year out of 365 days. What is the day of that year, latitude of the location, tilt angle of solar panel, then angle of declination for that place, and clearness index average, and reflection coefficient. Okay, so these are the things we have to say while finding out insolation at any location. So based on this, you can design a formula which I have not taken here, okay, to find out any insolation at any location. Okay, so there are many research papers available on how to find out insolation at any given location. Okay, so these are the main things we have to take into account Of course, the major thing is clearness index, because these other things are quite fixed, but clearness index and reflection coefficients, mainly clearness index, is the major factor where you have to which we have to take into account. So based on this insolation and this, by you taking this into factor, kind of a curve at a given place, any place, means I'm not particular about any place, but this is a kind of a solar insolation in kilowatt hour per meter square, or irradiance, we can say, irradiance versus day. So this is irradiance over a year, okay, available at any place. So this is how I know that how what is the irradiance available at a given place over a year. Okay, so of course this varies place to place. Okay, in north it is will be different, in south it will be different, in the extreme north it will be slightly different. Okay, and in extreme south it will be slightly different. East and west, of course it will different, and mid India or central India it will be different. Okay, so that will be the change in the solar insolation or irradiance. That's why the term irradiance is used. Okay, so this curve can be found out from this data. Okay, so once we find this curve, what will be the next step? What will be the next step?
Calculation, I think. We have to
Calculation. Next step is find what is load. Okay. Next step is find what is the load. Okay. What we'll do is we'll take one simple example. Okay. So how to find out a load? Of course, you must, or our electrical engineering background or some engineering background, so you must be knowing how to find out a load. But still, I will take one example of how to find out a load. Okay, so load calculations. Okay. So let us see again. We have taken very simplified example. So this is from, let's say, night 12 o'clock, that is I have taken 0 and 24, they are equal, okay, they are same, but still to divide a day in 3 phases. Okay, one is from night 0 to 6, early, then full day, morning 6 to evening 6, and then after 6 to night 12. Okay, so 3 phases I have divided into this load. Okay, so this load profile, we have to know what is the average load profile. Okay, of course this slide is not so simple. This is very plain load profile I have given. Okay, the actual load profile may be kind of like this. We don't know how it will be. Okay, so this can be a load profile. Okay, so of course you have to calculate what is the average of it. But for our understanding, what I have done is I have taken simple example, okay, of the plain load profile. Okay, did you get the point?
Sir, for the PV system, we have to shift our load also, because for designing a standalone system, we have to shift our load to peak load to non-peak load.
Yes, that is there. That's why I'm telling. See,
yes.
The actual load profile would be like this. Okay, so we don't know what will be the peak load, and we have to find out what is the peak load at a given place. Okay, for that. But right now, for calculations, what I am telling is, I am doing simple assumption that this load profile is plain. Okay, I'm not taking a complicated example. Is it okay?
Yes, sir.
Okay, I understand that. Yes, there is a we have to take peak load, we have to take everything, okay, into account. But that we have to we have now simplified like this. Okay, so let us assume that load 1, there are 2 types of load. Okay, we'll take only 2 loads. Load 1 is 48 watt, okay, for day and night continuous. day and night continuous. Okay. And load 2, okay, is, let's say, water pump, okay, which is switched on 3 times a day for 1 hour. Okay, 3 times a day for 1 hour each. Okay, for 1 hour each. Okay, so it 3 times a day for 1 hour each. So we'll distribute this water pump. So before sunrise once, before sunrise, after sunrise, and in a day, okay, once at noon. So like this 3 times it switch off. Okay. What is the load here? So this load here is, let's say, 4 ampere.
Professor, change the slide, please. Change the
Yes?
slide, please. Your slide is not changing. Please change the slide.
Slide is not changing. Again problem.
Yes.
Now you can you see now this slide? You can see.
Slide visual.
Sir, still slide at number 8, sir.
Okay, just a minute. I don't know why this problem is coming. Because I share entire screen, so I assume that everything is visible here. Can you see now?
Yes,
Yes, sir.
right.
Yes, sir.
Okay, so load 1, 48 watt, day and night continuous. Load 2, water pump, 3 times a day for 1 hour each. Before sunrise, after sunrise, once at noon. Okay, so this is 4 ampere at 24 volt DC. Okay, so this is the load. These are the 2 types of loads we have taken. Okay, so now let us plot in a day what is the load. Okay, so this is 0, 6, 18, 24. Okay, so first load will be continuous load, day and night. Okay, so this will be there, 48 watt load. Okay, or continuous. So this is 48 watt load. Other load is how much? 96 watt load for 1 hour. In the before sunrise, 1 hour.
Catherine, ma'am, please mute your mic.
After sunrise, means before noon, in the noon, and third is, so this is 1 hour. When it is not that important, the time is more important. Okay, the time for which it is on. Okay, so this is how much? 96 watt. Okay, 96 watt. 96 watt. Okay. So these 2 types of load we have taken into account. Okay. One is water pump load and other is continuous sum load, which is continuous there for 48 watt, okay, full day and night. Okay. So how will you now find out, okay, what is the day load and what is the night load? So there are 2 types of load, means 2 types of consideration. One is peak load and another is average load. Okay. So what is the peak load? Peak load is 48 plus 96. So in 3 times a day this load occurs. Okay, for 1 hour. 96 is how much? 144. Okay, 144 watt. And what will be the average load? What will be the average load?
Sir, 48 into 24 plus 96 into 3 by 24.
Plus 96 into 3 by 96 into 3, right?
96 by 24.
24, right?
Yes.
Correct? So 48 plus 96 upon 8, correct? So average load is nothing but, correct? Average load is 60. So this is the average load. Okay. So 48 is obviously there always, plus in addition to it, 12 watt load average over a 24 hours is there. Okay. Our peak load we have seen at a given time 144 watt. So these are the two types of loads we can find out. Okay. And then for battery purpose mainly, there are two types of current we need to find out. What are those is, one is peak current or maximum current, that is maximum load current, and another is IL average current. Okay. So from this we can find out, let's say there is a 24 volt battery for VB 24 volt battery. What will be the peak current?
Six amperes, sir.
6 ampere, and average current will be 2.5 amperes, correct? Average current will be 2.5 amperes. So there are two types of current. Okay, so ILM and IL average. So ILM will decide what is the peak current drawn by the battery, and IL average will decide what is the average current drawn by the battery. Okay, so these both figures are important to decide whether battery will be able to supply this much current in a given time. Okay, at a given time. So that's why these two figures are very important. Okay. So now let us go ahead with the next part. So we have now found out what is the peak load, what is the average load, and what is the maximum current or peak current required to be drawn from the battery, and what is the average current required to be drawn from the battery. Okay. Now next case comes for a standalone photovoltaic system, which is very important. Okay. So what is the next part? Next part is
Size of the battery.
size of the battery. So how will you decide the size of the battery? Just before going to the next slide, I just wanted to know how to decide the size of the
We
battery.
have to check how many days we have blackout.
Okay.
Sun is not available in a particular season or then, and that is also included, and total amount of ampere we have to supply in during that day also.
Okay. Okay. Fine. Good. So of course this is required. You are right. Okay. So we need to find out. Okay. What are the number of days for which the solar PV is not available, and number of days within which it will charge the battery.
Yes.
Okay. Again, we have to charge the battery. Okay. So these are called as this is called as autonomous operation. Okay. What is autonomous operation? Where, so this is called as autonomous operation, then solar PV is not available. So we have to always consider worst case scenarios. Okay. So days at for which it is not available are DA defined as days of autonomy.
Day of autonomy.
Days of autonomy. Okay. So once the battery, who will supply? Battery will supply for days of autonomy because solar PV is not available. We have to supply the load. So obviously the days of autonomy we have to consider the full battery will supply the load. Okay. Then once the days of autonomy are over, or assuming that they continues 2-3 days continuously, the solar PV the battery is supplying the load. Now let's say the solar PV is now again available. So we have to again recharge the battery to be ready for night load as well as next days of autonomy if it appears. Okay, again. So we have to recharge the battery. So this is called as days of recharge. One may think now days of recharge can be within 1 day. Okay, but what will be the problem?
The size of the system will be
Size of the
increased.
system will be very, very high. Okay, I mean, very high in the sense, okay, it may not be affordable also.
Yeah.
We may oversize the system. Okay, and of course, as we all know, oversizing the system is more area, so it will be quite costly affair. Okay, so we have to divide the days of recharge also in a given day with a given capacity. Okay, so days of recharge and days of autonomy, these things we have to consider. So how will you consider that? So first, let us say that days of autonomy are 0. Okay, first we have to consider basic battery size, where we don't need to consider these days of autonomy. So which load we have to consider?
Average load.
For battery mainly. Okay, so let's say this is a load. Load is mainly decided as day load plus. So this is load in watt hour for battery. So load for day. Okay, and you can say I'll write as WH day. Okay. Upon, of course, if you want to take battery efficiency into account, losses into account, so WH day upon battery and watt hour night on battery. But of course, if days of autonomy are 0, okay, for battery, main load becomes WH load is WH night upon provided DA is 0. Okay, so this is the main load which battery has to supply. Okay. Now, if the battery DA is not 0, okay, if DA is not 0, what will be the load? Battery has to supply. If DA is not 0, okay, then WH load will be, it has to supply night load.
Yes.
And plus it has to supply both day load as well as night load. Correct? WH day WH night. Okay, for autonomous days. Correct? Okay. So this it has to supply. Okay. WH night it has to supply, plus it has to supply for 24 hours, means multiply by number of days. Okay, so this has to be there. So this is the load calculation, or the battery capacity that should be there. Okay, so once we find out this is WH load, okay, so this is the load of the which battery has to supply when number of days, autonomous days are there, and then night load is there. Okay, so this is the total load. So what will be the ampere hour of the battery?
Divided WH load divided by the voltage of the battery.
Divided by
Voltage of the battery.
voltage of the battery. Okay, so this is ampere hour of the battery. Now one more factor we have to take into account. Okay, batteries generally, let's say lead acid batteries, and which type of battery we use is depth of discharge, is high depth of discharge battery. Okay, so let's say depth of discharge, or called as depth of discharge, or in short form it is DOD. Generally we choose 80%. Okay, if kind of battery we use for solar PV applications. So 80%, very high depth of discharge we use. So this depth of discharge also we have to consider. Okay, so this will also be there. Okay, so this will be the decide the ampere hour of the battery. Understood? Is it clear? Okay. Next part. What will be the next part?
Size of the
Size of the PV array. Okay. Once we know now battery size, we know our load profile. We have to now size PV array. Okay. We have to size now PV array. So there we have taken this one. Okay. So load profile plus day now autonomy, and two terms we need to know: depth of discharge and rate of charge. Okay. So we have to consider depth of discharge. So this we have to take into account. Okay. So now let us see how will be the PV array sizing. So what we will consider for PV array sizing?
I think we have to calculate, decide efficiency of the inverter also.
Yes, I have not. That's why I have said I have not considered it. Okay. Right now I am just considering this first three steps. Of course, there are many factors that comes under balance of system. Okay. Yes, right. You are right. Efficiency of inverter, efficiency of charge controller, everything we have to consider. Okay. But right now I am focusing on mainly battery and this one. Okay. So you are right. But I am not considering for simplicity. Otherwise, we will involve too many things. Then we will lose the feel of it. Okay, that's why I have not taken it. Is it okay?
Yes.
Okay. So for PV array sizing, what we'll do is there are three types. Okay. Which are the loads we have to consider? So watt hour day. Okay. Then night load. Which has to be stored in battery. Okay. And then
day of autonomy.
Exactly. So WH or autonomy. For autonomy. Okay. These three things we have to consider. Okay. So what will be the worst case?
Sir, if day of autonomy will be for the single day, charging in a single day, then the size the PV will be increased. So we have to divide the charging of
Yes.
the autonomy
Yes.
in
Yes.
days.
Yeah, we have to divide it. Correct. That's what we'll consider now. Okay. So this WH day plus WH night. So total load is WH day plus WH night upon eta B plus WH day plus WH night upon eta B multiplied by D. Correct? This is total load. As you rightly pointed out, okay, that yes, if you consider this load, it is too high for sizing. Okay, it means it will be oversized kind of thing. So what we have to do is this part particularly. Okay. So days of autonomy, the battery will complete the supply. So we have to replenish the charge or recharge the batteries again. Okay. So what we'll do is we'll divide that replenishing of charge in a number of days rather than one day. Okay. So once we replenish that charge, what will be the let's say those replenishing charge days are DR. Okay. So what will be that? Total will be WH day plus WH night upon eta B plus WH day plus WH night upon eta B DA, and we want to divide this into multiple days, so it will be DR, right? It will be DR. Okay, so this will be total WH load, or it will be PV array size. Okay, this will be a PV array size. So in this way, we can design the PV array. So once we know what is PV array load requirement, so the maximum power size required will be generally WH load upon there is equivalent hours for insolation, equivalent hours for insolation. Okay, it's the average kind of hours in a day. Okay, so we have to over a year, so these are kind of an average we take. Okay, so this upon this is energy and this is hours time, so we'll get power, okay, for a given PV size, because PV size is available not in watt hour, it is available in watts. So we have to find out the final size in watts. Okay, so this is how we can do the example. Now let us check with our example. Okay, so this is what we have found out. Okay, peak load and average load. Okay, so what is the day load for us? What is the day load for us? WH day is how much? If you remember, 48 watt for full day, right? And 96 watt for 1 hour, 1 hour, 1 hour. 1 hour before sunrise, 1 hour in the noon, and 1 hour in the after sunrise, after sunset. Okay. So WH day will be
Sir, for the PV, we have to calculate from 9 to 4 or 5.
9 to 4 or 5, or generally we take 7 to 5. Okay. So WH day will be generally 7 to 5. Let's say 7 sunrises and 5 sunsets. Okay. We can take like that. Okay. Of course, it varies from place to place, but and time to time. But let's say 7 a.m. to 5 p.m. So how many hours? 10 hours, correct? So WH day is how much? 48 multiplied by 10, correct? Plus
90 plus
96
1 plus 1 into 1.
1. Okay. So 480 plus 96. So it will be kind of 576, correct?
Yes.
576 watt hour. This is WH day. What will be the WH night? So 48 multiplied by 14
14 plus
plus
96
96 multiplied by
2.
so it will be kind of 48 480 plus 96 plus 96 plus so 480 plus 96 into 6. How much it will be? So this will be around 980 plus 76, 1066, correct? No, 1056. Correct? Okay. So this will be 1056. Now, what we have to find out, we have found out WH day and WH night. Okay. But of course, for WH load in the night, we have to also consider battery efficiency. Okay. So we have to always consider the battery efficiency. Let us take battery efficiency as for our purpose 0.8. Okay. So this will be kind of 0.8, and this will be around how much? How much it will be? So let us take a calculator. 1056 by 0.8 will be 1320. So this will be 1320 watt. Okay, so this is WH night. Okay. What we are doing is battery sizing. Okay, so battery sizing is this. So what will be the battery sizing? Let's say days of autonomy are 2. Okay. So what will be the battery sizing total? Is WH night upon eta B plus WH day plus WH night upon eta B multiply by So this will be the, so 1320 plus, how much will be this? WH day. WH day is given as 576. 576 plus WH night is how much? 1056. Plus 576 upon 0.8 multiply by 2. So this comes as 4080, right? So total WHB comes as 5400 watt hour. Okay? Is it correct? Yes, the person, the professor who is speaking in between. Is it correct?
Yes, sir.
Okay. Can I know your name, sir?
Sir, Avinash Kumar. I am a PhD scholar, sir.
What is your name, please?
Avinash Kumar.
Avinash Kumar. Okay. Avinash Kumar ji, please respond. Okay. So, okay. Is it correct till now?
Yes, sir.
Okay. Any other candidate also, please, any other participants, please respond. Otherwise, I feel like nobody is there and just I am speaking. Okay, because even though it is online, please respond. Okay. So this is 5400 watt hour. Okay. Now what next? PV array sizing. We have now found out battery. Okay. Of course, we have not completely found out. Now let us say that there is a 24 volt battery and a DOD of 0.8. Okay. So 5400 by 24 by 0.8. Okay. So this will be the ampere hour of the battery. 5400 by 24 by 0.8. So what will be the ampere hour is 281.25 ampere hour. Okay. So this will be the ampere hour of the battery required. Of course, the single battery just cannot be. There is a array of batteries we have to use in parallel and series, okay, to achieve this ampere.
I think 3 battery of 100 Ah is required in there.
Yeah. Of course, now, what you said, Avinash?
Sir, we have, it's not a common battery because we have to consider 300 Ah. We have to consider.
Yes. Of course, we have to use a battery which in parallel and series.
Yes.
To achieve this. We cannot have a standard cell. So it's a design, right? We need not be accurate. So it can be mostly on higher side. Let's say 300 ampere hour. For slightly oversized, we have to do all this. So, as all of you are from engineering background, you always know that design always will be something different. It should not be always accurate in the sense you have to always do some oversize. So of course we have to use 300 ampere hour or 300 ampere hour in parallel like that. So this is the battery size. Now next part is array size. So already we know what is night and day and night. Okay. So what will be the array size? So array size is WH day, again I'll repeat here, plus WH night upon eta plus WH night, day and night, upon eta b multiply by autonomy upon recharge.
Detail.
Okay. So assume that D recharge will slightly higher, let's say 3 days it takes to recharge. Higher the recharge, lower the PV size. Okay. So what are the WH day we have found out? WH 576, then WH night is 1320. Okay, and this is total is 4080 if we multiply by DA everything. Okay, so this is 576 plus 1320 plus 4080 upon 3. Okay. So this will be 4080 upon 3, 1360 plus 1320 plus 576. This will be 3256 watt hour. What will be the solar PV size? If you say H at mean,
About we have to divide with by 4.5 watt hour kilowatt hour with
yeah.
average installation is about for the 1 day generation for 1 kilowatt
Yeah.
is about 4.5 kilowatt hour.
Yeah. 4.5?
Kilowatt hour.
How?
It's for the Indian scenario we have to consider we are considering about 4.5 kilowatt hour for the 1 day generation for 1 kilowatt power plant.
Okay. I'm just seeing the irrespective of Indian situation or all. Okay. I'm just seeing what is the actual load calculation. Okay. Based on that, I am sizing this. So let's say H at min is 5 hours. Okay. Then this will be, what will be the PM? Should be greater than 3256 upon 5 watt hour upon hour. Okay. So this will be 651.2 minimum watt. Okay, minimum. So it should be higher than this. Okay, to take care of all other things, like we have not considered many efficiencies still. Okay, but this is very crude design I have done, but just to give an idea how it should be. But these are the main factors we have to consider. So this is how we arrange. Of course, there are some more things are left here. Which are the things I have left? Now, if based on module, based on this wattage, we can decide the area. Okay, area of the module, everything we can decide. Okay, of course, then we have to use this insulation equations, as you said, Avinash. Right? Decide the area. So this is how we have to design this. So now I will come to next part. So this will be PV array size. You might be knowing, I'll just quickly go through it. Series and parallel connection. So as we know, when we connect in series solar PV, then the open circuit voltage is added or voltages gets added and the current remains same. And when we do in parallel connection, the current adds, the short circuit current adds or total current adds, and the open circuit voltage remains same. Okay. Now what will be what do you mean by MPP? Okay. So for understanding MPP, of course, you might be, many of you might be knowing, but just wanted to share some interesting parts again, which might be a revision for you also, some of you. But I want to show you from the circuit theory point of view. Okay, how you will find out MPP. So when you see PV panel is a source, okay, it is which source? It's a voltage source or current source?
The current source.
It's a current source. Are you sure? That's the dilemma. Okay, so dilemma. It's a current source. Of course, we model it as a current source. Okay, like you have seen. This is the model of a. What is the model? This is kind of a model, right?
Yes.
We use for a PV. Okay, but this is neither current source nor a voltage source. Okay, we can always vaguely say this is a power source, or we can say that this is a power source. Okay, solar PV is a power source. If it is current source, then it should be always giving current. But why we connect capacitor across it? Right? Most of the time we connect capacitor across it.
Yes.
Right? But this voltage is also varying, current is also varying as per in the insolation. Voltage of course varies very little, but current varies very significantly as per the insolation. Okay. But when we see from here, from the external world to this PV source, okay, so how we study the PV, any external, from the external world, any circuit, we study its voltage and current characteristic, correct? We study its voltage and current characteristic. So when we consider this as a source, so we can say that the current, from the source generally we take current characteristic coming out of the solar, means any source. Okay, so this is a source. Okay. When we see from the circuit point of view, okay, first characteristic we study V and I. So let us see what is V and I characteristic of a solar PV. Okay, the first thing we do is, okay, can we short circuit this? Okay, we short circuit this. If we short circuit this, does it flow, does it pass infinite current?
No.
No, it pass some current. We can say it as short circuit current. Okay, if we take this as a IV curve, okay, so it passes some current which is called as short circuit current. ISC. Then, when we say this is open circuit, okay, so that is so infinite voltage?
No, it's limited.
No. So then it is not current source, correct? Can you make open, leave current source open? No, correct? You cannot leave current source open at any time. So that's why we can say it is neither current source nor a voltage source. Okay. So we can get some finite open circuit voltage. Okay. Then what will be our next study for a given source? Our next study will be, we'll connect some load. So we know that this is a DC load. This is not this is a kind of a DC source, right? This is we are confirmed. So when we study this, let's say DC source, so what we generally study, the most normal circuit element we use is to study the thing is resistor, correct?
Yes.
So resistor we'll use. So for any IV curve, okay, or any IV plane, when we say very high resistor, then resistor will be towards, so this is R, okay, it towards very high, and when we say very low resistor, it is near I axis, correct? This is R low. Okay. So this will be the resistance. So when we vary the resistor, we get a locus of this resistance of this V and I. Okay. So we get this kind of locus of this variation for a given insolation, okay, or we say radiation, or given irradiation. So we let us say consider 1, that radiation. Okay. So when we vary the radiation, then what we'll get? We'll get different kind of similar characteristic, okay, as per the variation of resistance, but for short circuit current of different values. Okay, for short circuit current of different values. That variation we get with a varying, let's say this is 0.8, this is 0.6, like this. For different kind of variation in solar radiation, we get this kind of current, but the type of characteristic is similar. Okay, the shape of this curve is very similar. Okay. Now, when we vary this resistance from 1 to high, okay, let's say from low to very high, what will happen? One point comes. So again, let us go back to the curve here. Okay. When we vary this resistance, one point comes here at which the product of V and I is maximum. The product of V and I is maximum. So that resistance is cutting the curve of here. Okay. So why I am taken from this resistance curve from the origin? So what will be the operating point? The resistance curve and PV curve. Where they cut each other, that will be the operating point of V and I, or the total system. Okay. So that's what is happening. So when this resistance is moved from one, like from low to high or high to low, one point comes where both the product of V and I is maximum. Okay, so when you plot this product of V and I is maximum, so you get here the maximum power before and after which the power is lowest, the lower. Okay, it gets lower again. So this point is maximum. So that point is called as maximum power point. Okay, is it clear? Of course, you must have seen this earlier, but this is the way we can find out a maximum power point. But of course, in practical system, you cannot vary resistance just like that, correct?
Yes.
Can you vary the resistance?
Load is constant.
Okay. Huh?
Load is always constant with.
That's why?
That's why we can't change resistance.
We can't change resistance, correct? Load is fixed. We cannot vary load. Right? If you are giving some load, we cannot vary that load. Correct? So what we can do then? What is our first goal?
We have to collect maximum power from the PV.
To achieve the, of course, we want to extract the maximum from the system. Of course, it is also should be remembered that in some systems, okay, MPP may not require at some point of time. Okay, of course, there are some systems where MPP may not require at some point of time. At that time, we operate the system at non-MPP. But most of the time, we operate system on maximum power point. Okay, but load is not in our hand. Okay, load is not in our hand. So what is our goal is, our goal is this V and I, when you connect this to external world, solar panel, when you connect this to external world, okay, the equivalent resistance seen, that is R is V PV upon I PV. So this is V PV, and I should be such that it should operate at this maximum power point. Okay. It should operate at this maximum power point. But it is not always possible, right? It is not in your hand that you will always be checking at what point the resistance, or you have to adjust your load such a way that it should be like this. Okay. Then how will you do it? That is our next question. Okay. Did you understand the definition of the problem?
Yes.
That we have to find a load such that this operating point should be at maximum. Okay. Or not load, the R, the equivalent R, or this solar PV panel should see resistance connected to it, because this is a DC source. Okay, I am not saying either is a voltage source or current source, but this is a DC source. So DC source should see equivalent resistance such that its operating point it has maximum power. So this is our problem definition. Now how will you achieve that? So that is our next part. How will you achieve that? Any idea?
Maximum power point tracking system.
Yes, that is there, but there is some to operate that. There is, of course, there are algorithms to do that, but there are means to do it, right? That is algorithm. But how will you do?
So by equating the internal resistance with the load resistance.
To connect connecting the.
By equating the internal resistance with the load resistance.
Which internal resistance? Oh, you are talking about maximum power point here.
Yes, sir.
No. Don't confuse with that. That is
Okay.
not. That is different. Okay. What I am talking here about, there is no here. You are not this solar PV source is not defined as our conventional voltage source in series with some resistance. Okay. You are confusing with that. Okay, because what is the characteristic of this source? Let's say you want to check VI characteristic of this. What is the characteristic?
So planar characteristic.
V and I. So which is characteristic is like this, correct?
Yes, sir.
If you take, right? Its correct is like this. But what is our characteristic of here? Here, it's like this. So this doesn't is not the way. Okay, to find out the answer. So this is totally different.
So to get
with
the
the current
maximum volt, our motive is to get the maximum voltage.
No,
From the-
we are not maximum.
We have to, we have
Maximum voltage is VOC.
minimum series resistance and maximum shunt resistance. So we have to maximum shunt resistance that can be helpful to
See,
improve.
when we see big solar PV system, they are operating on MPP. Okay.
Yes.
Who will control that resistance?
That MPPT system.
MPPT system. But by using what?
So instantaneous voltage and current measurements, and then finding the product and checking whether it is maximum.
Yes, correct. You are right. That is done by computer. But in hardware,
Yes, sir.
somebody has to do it. That is in computer, and the computer will give command to something else to achieve that. You are right. So there, of course, there are power electronics converters comes in picture here. Okay. So I'll take one simple example so you will understand. I hope you all know boost converters.
Yeah.
Okay. So how to achieve this boost converter? Okay. How to achieve this by using boost converter? So let's say there is a resistance called RMPP, okay, which is a EMP upon IMP. Okay. So this we have to achieve this RMPP. So let us study the solar PV panel is connected to a boost converter. Okay. Is connected to a boost converter. This capacitor will be generally there, this shunt capacitor, but that is to filter the noise mostly or ripples. and it is connected to a boost converter. And this is your load, which is variable. This is variable, this is load. Assuming that this load varies such that the boost converter will always in CCM, okay, for our convenience. Boost converter will always in CCM. So input voltage is VPV and current is IPV. Okay, VPV and IPV. So output voltage is some V0. Okay. Output current is I0, which is V0 upon this R load, correct? So I0 is V0 upon R load, or R load is nothing but V0 upon I0. Keep this equation in mind. What is the relation between V0 and VPV? 1 upon 1 minus D. Remember? 1 upon 1 minus D, where D is a duty cycle of a switch. I hope this I don't need to explain to you, correct?
Yes.
Okay. Now D is a duty cycle. What should be the internal, what is the resistance which is seen by the solar PV? VPV upon IPV is nothing but R in, correct? Yes or no? The VPV upon IPV is the resistance seen by solar PV panel. Okay. So now, what is the relation between I0 and IPV? Again, 1 minus D.
1 minus D into 1 minus D.
Okay, I0 is 1 minus D into IPV.
IP.
So then, now substitute here V0. What is VPV? V0 upon 1 minus D. Okay. What is IPV? Sorry, V0, VPV is nothing but V0 into 1 minus D. What is IPV? I0 upon
I0 by 1 minus D.
Correct. So what will be R in? V0 upon I0 into
1 minus D, the whole square.
minus D whole square, which is nothing but R multiplied by 1 minus D whole square. Correct. So RL is RL into 1 minus D whole square is nothing but R in. So if you want that RL is not in our hand, what is in our hand? Duty cycle, correct? Duty cycle is in our hand. So we have to vary duty cycle in such a way that R, it will be okay, at some duty cycle for a given load. So it is kind of a DMP for a given load. If load varies, this also will vary. Is it clear?
Excuse me, sir.
Yes.
Yeah, actually here we are not taking the efficiency of conversion in boost converter, no?
I am assuming this is ideal converter.
Okay, sir.
I have to illustrate the concept of MPP, how to achieve MPP. Okay, algorithm is another thing, but algorithm will give command to something, right, to achieve that. So this kind of actuator This DC to DC converter is an actuator. Control is inside the computer or the microcontroller. But who will achieve that or who will actuate that? DC to DC converter. Through what? In DC to DC converter, it is achieved by duty cycle. Boost converter is one example. There can be a buck boost converter as well. There can be a buck converter. There can be multiple number of DC to DC converters. Is it clear, this part? Okay. Any doubt in this till now? Avinash, any doubt?
No, sir.
Okay. So this is how we achieve. Okay. The control parameter is duty cycle. Okay. So DC to DC converter and load. Of course, when we use directly inverter connected to this, if you say, let's say inverter, this, then of course the modulation index is the one which we have to control the MPP. Okay, so PV model will see kind of from the DC link, DC current only, but inverter modulation index will achieve the maximum power point. Okay, so there are multiple algorithms for this. You must be knowing about it. I will not discuss this because you already know about this. So perturb and observe. You know about these algorithms, right? Incremental conductance, ripple correlation, many other algorithms. Okay, you know about it or no? Okay, so I will not.
Yes, sir, we know. Yes.
So I will not go into it. We will now go to interesting part, which is simulation. We'll see. So let's say I'm using Plex. Can you see the simulation screen?
Yes, sir.
Okay. So this is a PV panel we have, and this is taken from the model BP365. Okay. So this has a 65 watt panel, 65 watt, okay, and 17 point something around 17.5. It's is its voltage for maximum power point. Okay, and based on this 3 points, I think 65 by 17.5. So whichever is the current, it's 3.74. IMP is 3.71. Okay. So these 65 watt panels are two connected in parallel. So this is what it is done here in this simulation. You can see here this is a PV model. So two connected in series, two connected in parallel. Okay, so total voltage is around 36 MPP voltage, and MPP current is around 7.6 something. Okay. So this is the PV panel. This is a boost converter. Okay. I have taken some into account some resistance, but it may not be required also. Just to illustrate, these two loads are taken. After some times, this will come in picture. Okay, this 20 and 20 watt. Okay. This is the MPP algorithm is implemented here. In this, you can see this. This is the code where the perturb and observe algorithm. The output of this perturb and observe algorithm is a duty cycle. Okay. So before going further, we'll do some calculations here, so that simulation will not be always blind. We should know what is happening. Okay, with the simulation. Before doing the simulation, we should be ready with the calculations, our own analysis, and then that should be verified with the simulations. Okay, so that is the main requirement for us. Okay, so what we'll do is we'll do some beforehand calculations. Okay, So what will be our resistance for this? What is the RMP? What is RMP? So RMP is, we know 17.5 approximately we are finding out upon 3.71, so which is around 4.71. So this is our RMP. Are you getting what I am talking about? Are you getting what I am talking about? Okay. Now what is our load here? Our load is initially how much? 20, right? 20 ohm. Okay. So what is our for MPP? What should be the duty cycle? That is our first problem. Okay. So if RMP is given as 4.71 and RL is given as 10 or 20. So 1 minus d square, RL is 20. What will be the D? What will be the D? So 1 minus d square, okay, upon 4.71 upon 20. How much it will be? By 20. Okay, its square root. Then plus 1. So it will be around 0.5. So D comes around 0.5. Okay. After some time, the load is changing from RL 20 to 10. So if RL is 10, but RMP remains to be same because for a given radiation. So what will be the new D? So this will be D1 is 0.51 and then D2 will be, again we have to do the calculations. Okay. So 4.71 upon D, that is 10, square root. Okay. And plus 0.3. Let's check whether this is working. Okay. So what is happening here is this is 20 ohm. After 2 seconds, okay, let me make it 3 seconds or 2.5, half the simulation. This simulation will run for 5 seconds. Okay. And after 2.5 seconds, the parallel load will come across it, and this will be total. How much load is this? Will be around 10 ohm. Okay, so we have to find out what is the duty cycle. So for finding out duty cycle, we'll correct here. Yes. So this is duty cycle, which is the output of the MPP controller. Okay. Now I will show you again simulation. It is finished very fast, so that's why it is. Can you see the point, operating point moving around the curve? This is the point. I'll again run the simulation. Can you see this point, small point? I'll run again. Can you see this small point moving here?
Yes, sir. Yes, sir.
Okay, so this is working around MPP. Now let us see whether the voltages and currents are following that, what we have can do. So we can see here, what is our MPP voltage is around 35. So it is around 35, correct? right? And our current is around 7.5 or something, or 7.34. So it is around that point, correct? Right. So that's how we do. Then our main interest, what we have found out, is our duty cycle. So let us find out whether duty cycle is following it or not. Okay. So what is our first calculation is 0.51. So it is around 0.51. Correct? Can you see this? This is around 0.51.
Yeah.
Right. And our next calculation was 0.31. So let us check whether it is around 0.31. Correct?
Yeah.
So this is how. First we should know what we want to see. Okay, or our analysis should be ready. Then only we'll realize, okay, if simulation is correct or not, what we want to see. So our understanding of the system is clear, then simulation will be actually to validate that we can do the simulation. Okay. I hope you understood what is how to find an MPP and this upper point, given point, and how to achieve it. Is it clear? Okay. So in this way we can do the things. Okay. Now let us look into briefly this PV system. Okay, I have not simulated here. Okay, but this is a general typical PV system which we have. That's how we implement it most of the time. Okay, we have seen the general diagram in the beginning, but this is actually a typical diagram. Okay, so our standalone photovoltaic system. So this is a battery. This is a battery charge controller, which is two-way. And then this is the solar PV system. So this is connected to a boost converter. So of course there will be unidirectional power flow from this side, which is PPV. Bidirectional power flow from this side, this is PB, battery flow. So battery, whenever PV power is low, battery will supply rest of the power. When PV power is 0, battery will supply whole the power. Okay, and then this is load side. Okay, so this is how it works, and this is a bidirectional DC to DC converter, which is either charges the battery or discharges the battery. Also, this bidirectional converter will maintain this voltage here constant. Okay, so the load voltage will maintain constant. So all control system will be implemented in battery bidirectional converter as well as the PV unidirectional converter. Okay, so in this way we generally implement the practical systems. Okay. So this is how we can give the idea. I think now time is also over. Okay, so now if you have some questions, you can discuss or we can stop here. Okay. So thank you. I hope you have understood the gist of the how to go about in a standalone photovoltaic system. Arvind ji, any?
Yeah, I'm listening. So now session is open for discussion. If anybody has any question, please ask. Hello?
Yes, sir.
So I hope.
Yes.
Anybody asking anything? Please ask.
Yes, somebody asked something.
I hope I think you have answered all the queries in between.
Okay.
So first session was interactive.
Yeah. I would like to have always interactive. Yeah. Otherwise, I feel like very boring. I myself feel like boring. Like there is not.
Sir, is that what is the software name, sir?
It is a Plex.
PFL?
Software, Plex, PLECS. It is particularly designed for power electronics.
Okay, sir. PLCF, it is a free downloadable or?
It's not free. It's our institute has a license, so that's why we have.
PLCF. Okay, sir.
Use other softwares, NG
Okay,
Spice.
sir.
Okay, so this is a free open source software. You can use it.
Free Spice.
NG Spice.
NG Spice. Okay, sir. Okay, sir. Thank you. Sir. Thank you, sir.
Yeah.
Okay.
I hope it is
So,
enough informative to you about the standalone.
Yes, sir. Yes, sir. We can
so
able to
I
design.
hope,
Yes, sir. Thank you.
Yeah. Thank you.
right. So, Dr. Amod, I hope everybody enjoyed that session and it was quite informative as well as calculated and useful also. So, in nutshell, I can say it was very impactful lecture and definitely everybody will be benefited from it. And once again, I would like to pay my sincere thanks to you for requesting our invitation and sparing your valuable time. I hope in future also I will get the same response for you. So from my side, thank you very much and best of luck.
Okay. Thank you, sir, for inviting me. Okay. It was quite nice time to interact with you.
Yeah. Thank you very much. Okay.
Yeah. Thank you. Yeah.
Okay. Now you can discuss.
Yes, sir.
Okay. So, and dear participants, now time is 1:15. So again we will connect at 2 o'clock, right? So we will meet at 2 o'clock for the further sessions.
Okay, sir.
Okay.
Okay,
So
sir.
enjoy the lunch and we will meet after lunch.